Hey guys, welcome back to Learning Kotlin Live, and this is the episode 56. So, last time we talked about coroutine contexts and dispatchers, and yeah, it explains a lot of the mysteries of Kotlin. So that there is an attribute of every coroutine, and one of it would be dispatchers. And let's take a look at this example. So we can see that this and this are run on thread main, and this is run on default dispatcher, and this is run on our own thread. So without specifying any dispatcher, basically everything would be run on main. And why is this run blocking? Oh, it's run blocking because the outer scope of this coroutine is run blocking. So without specifying any dispatcher, that we're going to use the inherited dispatcher as default. So let's still call it default because we're going to use this term later. So you're going to inherit from your parent anyway. So because run blocking is the outer is a dispatcher or the because run blocking builder would transform a block into a blocking coroutine which runs on the main. So that's why we're seeing this main run blocking. I'm working in thread main, blah blah. But why is it listed as the third item here? So that is because unconfined and default are executed earlier. And why is that? Basically, this would be dispatched to the main thread. So after every line of this is executed, only after after every line is executed, this the internal this run blocking parent will unblock, and so that is when the child would be able to use the main thread. So that's this case, and this coroutine 2 is this coroutine, and this is coroutine number 3. I would say yes, it's unconfined, and it is dispatched on the unconfined dispatcher, which is also the which means that unconfined. Where's it? Unconfined. It's a special dispatcher that runs on the main thread, but it's a little bit different, and here's why. Because I think it's only running the first. Yeah, so this means that it is still dispatched on the main thread, and it gets the priority until the first suspend point. And the only suspending point in this coroutine is the end of the coroutine. So basically, it gets the priority of main thread, and so it is executed first, even though it is created later. And also, there's a dispatcher.default one, and because it is on another thread. So while the parent of these coroutines are still blocking the main thread, this can be launched first as well. As for why launching on a new thread is slower than this main coroutine, my guess is simply the creation of this thread takes too long. That's just my guess. I have totally no idea what's happening here. A dedicated thread is a very expensive resource in a real blah 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 blah. Nope, it didn't talk about why, but that's my guess. So here we talk about, last week we also talked about the difference between unconfined and confined one, and I think this parent is run blocking as well. Yeah, it's run blocking, so this is going to inherit the run blocking, and this is unconfined, so there's a delay here, so I think this will happen first because this gets the priority and it lost the priority, and after that these two will probably come in. I don't know. Unconfined and probably later this one, and I don't know this one and this one which one is first, but I'm pretty sure this is going to be first and this is going to be second. So yes, I'm working in thread and I'm working in thread, and after that delay, because that delay itself is long enough, so probably it's going to be unconfined and run blocking. And yes, and well, one of the very important thing you need to notice is, you see that after delay in thread, the coroutine which is dispatched it on the dispatchers.unconfined, it is executed on the default executor instead. So I think there's a special note that unconfined dispatcher is an advanced mechanism, so it's usually you only use it in special cases. So debugging coroutines and thread. Okay, this is just something talking about that. Oh wait. Oh okay. There's nothing. It's only talking about that when you add the -d Kotlin x.coroutines.debug JVM option, everything is going to be executed on the you get these debug messages when anything is logged. So jumping between threads, is this where we left last time? I don't know. I think yes. So yeah, we're going to start from here for today's lesson. So let me first check if I always forgot to take a look at if there's anyone in a live chat. Let me take a look. So nope, I don't see any live chat, so I'm going to move on. So jumping between threads. So if you feel like I'm speed running these contents, that is because I have already covered these in the episode 54 of Learning Kotlin Live. So if you feel like that's too quick, just take a look at that video. And so run the following code with there's a access control exception due to security reasons in Wave Web Playground. Modify thread. No, it did not cover this. So this is basic. This is probably an something that is not expected. I don't know. But so let's take a look at this. Oh, there's a usage should be marked with. Oh, this is interesting. Okay, I'm not going to take a look at it now. But there are just warnings, Kotlin warnings. So new single thread context. Oh, this is something that is new as well, because we only learned about dispatchers, and now we're going to take a look at context. New single thread context dot use ctx1, and that's a lambda. Oh, this is so difficult. It's so hard to take a look at. So basically, new single thread context and single thread context, and the run blocking and the with context here, and there are a lot of log. And let's look at the result. So this is the context one, and there is only one coroutine. Okay. It demonstrates several new techniques. One is using run blocking with an explicitly specified context. Run blocking and with context. Probably that's what. Oh no, this is what it's talking about. And the other is using with context function to change the context of coroutine while still saying in the same coroutine, as you can see in the output. Okay, so yeah, it's always in coroutine 1. So we have a single thread context and blah blah blah, and later this is dispatched blah blah blah, and there's a run blocking with context 1, and started in context 1 is logged in this run blocking. Wait. Oh, started in context 1, which is this one. So it's CTX1, capital CTX1. And later something is with context CTX2, we log. So it's working in CTX2, and CTX2 should be this capital CTX2 as well. Yes, there it is, and here it is. And after that, it switches back to CTX1. That's my guess. Yeah, so the message here is back to CTX1 as well. So this is a lot, but I think the concept behind that is simple enough. So note that this example also uses use function. Where is it? Here. From the Kotlin standard library to release threads that are created with. Okay, so use is basically just a way to release something. Give me the use. It's not giving us a use, but you can, with this we can see a use. No. Not found. I need a use. Where is use? No, there's no use. Anyway, it doesn't tell what. Oh, it's extending coroutine dispatcher. And is there a use here? Nope. And it is interceptor, so is there a use here? No, but it is not extending anything, so I'm lost. How about, oh no, it's definitely not closable. So can't find what that use, where that use is declared now, but basically that use is just to give the context the scope of where it should leave, how long it should leave. I kind of feel like this should be covered first. I always feel like these coroutine tutorials are jumping here and there. It's not perfect yet. So the coroutine's job is part of its context. The coroutine can retrieve it from its own context using coroutine context job. Okay, it's a hash map. My job is coroutine context job. So the context is blocking coroutine, and okay, that's what the run blocking gives us. Blocking coroutine active at blah blah blah. And the coroutine name is coroutine number 1. And it is of type blocking coroutine, and its status is active, and this is probably its hash. So it produced something like what when running in debug mode. Yep, we talked about this already today. My job is blah blah. Now that is active in coroutine scope is just a convenient shortcut of okay, so okay. Well, I never used this, and he told me that you should take a look at this. This is nonsense. Children of a coroutine. So when a coroutine is launched in a coroutine scope of another coroutine, if you launch a coroutine in another coroutine, it inherits its context. And the job of the new coroutine becomes a child of the parent coroutine's job. When the parent coroutine is cancelled, all the children are recursively cancelled too. Yep, that makes sense. So that's part of the something concurrency that it mentioned. Let's take a look at it. I think it's here. Yeah, structured concurrency. That's the naming. So it talk about how you can cancel things in a child way. That is something that is not very possible with Java. I think that's what it means, basically. Where were we? Here. Hey, wait. It inherits its context via coroutine scope, coroutine context, and the job of the new coroutine become a child of blah blah blah. However, when global scope is used to launch coroutine, it is not tied to the scope it was launched from and operates independently. So you can use global scope anytime. So basically this here launches, is this in the run blocking as well? Yep. So the context of this launched coroutine would be blocking coroutine. Let's see what we have here. It would be, or is that blocking? Oh, here it is. It would be coroutine number 2 blocking coroutine active. I'm not going to guess that active actually, but it's always going to be active, I guess. And this context would be global scope coroutine context number 2. I don't know. So because these are, there's a launch. So this would be launch on another coroutine, and it is run in global scope and execute independently. This is going to come first. And this is going to come later when this launch is dispatched. When this coroutine is scheduled and this coroutine is scheduled, and then after the resource of these blocking is unlocked, this launch here would where it would continue, and this job 2 I'm a child of the request coroutine would move on. And also because everything is run blocking, so after 500 milliseconds the request is cancelled, and these two, this is going to continue. It's not affected by cancellation, but this will be affected. And who has survived request cancellation? I think this is going to survive as well. So basically it's going to be job 1 global scope, job 2 I'm a child, job 1 I'm not affected, and who has survived. That's my guess. And bang, global scope, child of the request, and not affected, and who have survived it. Yep, that's everything it would like to cover. Parental responsibilities. Wow, that's look like a topic of life rather than coroutine. A parent coroutine always waits for completion of all its children. So if you are joining to thread, you're joining a thread with a coroutine, you need this job.join, but a parent coroutine always waits for the completion of all of its children. So it's going to live as long as its children are not finished or cancelled. So request launch, repeat 3 times, and a few children are launched, and request. So basically there are a lot of blocking coroutine which are which repeats for 3 times in that coroutine. So it's going to delay for it's going to launch 3 coroutine which are again blocking, and it delays for 200 milliseconds, 400 milliseconds, and 600 milliseconds, and it's going to say coroutine 0 is done, coroutine 1 is done, coroutine 2 is done. So because all of these are blocking, so request I'm done, and I don't explicitly join my children that are still alive. So this is going to come first, and this is going to come for 3 times. Coroutine 0 and 1 and 2 is done, and because it waits for everything including its children, and now the request is complete. Yep, so I actually don't know what this chapter would like to cover. I think it's basically even if you have not joined this launched coroutine with this blocking outside coroutine, it's still after everything is scheduled, it still waits for everything is every children to be executed before it is recycled. But for global scope, it's probably not that case without you joining that global scope coroutine. Naming coroutines for debugging. I don't know if I can finish this chapter today. So this looks pretty simple. You just give it a coroutine name and it's just for debugging. Automatically assigned IDs are good when coroutines log often, and you just need to correlate log returns coming from the same coroutine. However, when coroutine is tied to the process of a specific request for doing some specific background task, it is better to name them just for debugging purposes. Serves the same function as the thread name, and it'll get displayed in a thread. So v1 coroutine and v2 coroutine, and the answer for v1 divided by v2 is v1.await, v2.await, and because it is delayed for a while, so it's going to be computing v1, computing v2, and the answer. And what is even more important is because we are using this log function here, so we can know the name of the coroutine. So the name here would be v1 coroutine, and this would be v2 coroutine, and this would be the outer blocking coroutine, which is main. And because it's on also the blocking coroutine made by the run blocking is called, oh, there it is. It's called main because we pass it in. So add main number 1, blah, 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 and that's it. Combining context elements. Sometimes we need to define multiple elements for coroutine context. We can use plus operator for that. For example, we can launch a coroutine with an explicitly specified dispatcher and a specified name at the same time. So we can give it a dispatcher.default, that's the dispatcher, and coroutine name is the name, the coroutine name, and we call it task. So when you run this, you would see I'm working in thread, and let's take a look at the current thread name. And it would be, if you have debug on, you will see I'm working in thread. And here's the default dispatcher, here's the dispatcher, and here's the name, which is add test. Number 2, where does this number 2 come from? I think there are multiple coroutines with the same name. This is, I don't know how the ID, the number after the name, get assigned. Is it always is the ID pool shared, or only shared when the name is the same? I think it's always shared, right? Well, it's not illustrated here. Maybe here. Yeah, it's for this case it's always on main, so no, we still don't know if the rule of it. And yeah, here's the coroutine 1 is reused, so no, I don't know, but let's skip that number. We just need to know that this is an identifier for a coroutine, but I don't know the scope yet. So coroutine scope. Let us put our knowledge about context, children, and job together. We talk about dispatcher. We talk about context, but context to me is just more like a name. Children and jobs, yes, we talk about these. Assuming that our application has an object with a life cycle. But that object is not a coroutine. For example, we are writing an Android application and launch various coroutines in the context of an Android activity. Okay, this is so Android. To perform a synchronous operation to fetch and update data. Activity in Android are just like a window that you can see. And when basically it is a window of your application, and the UI is always on it. So like when your application is in the background, which means um, no activity is shown. It kinda needs to be it changed state. It's not always recycled, but it's going to change state for sure. So perform asynchronous operation to fetch and update data, do animations, etc. All of these coroutine must be cancelled when activity is destroyed to avoid memory leaks. So when you go to background, you don't always. So in Android world, activity has its own life cycle, which is created, started, resumed, and also paused, stopped, and destroyed. So the creation is the very beginning of the life cycle of an activity, and every activity should only receive that once, basically. And so that's why when things are destroyed, all the resources that you have clinged to during the life cycle of activity should be recycled, and coroutine should not be an exception. So a common mistake that is often made in the Android world would be if you started a thread and the thread is still working, and after your activity was destroyed, the thread is still there, and that's not a good practice. So we of course can manipulate context and job manually to the activities and coroutines lifecycle, but Kotlin X coroutines provide an abstraction that encapsulate that coroutine scope, so you can build something that extend on it. So class activity, and there's a main scope. You can just create a coroutine scope that should be attached to this activity, and when destroy is caught, you just cancel everything on main scope. That's the purpose of coroutine scope. We manage a life cycle of our coroutines by creating an instance of coroutine scope that is tied to a life cycle of our activity. Well, it is tied to this activity because it's a member of that activity. Coroutine scope instance can be created by coroutine scope or main scope factory functions. I don't know what's the difference between these now. The former creates a general purpose scope, while the latter creates scope for UI applications and use dispatchers.main as a default dispatcher. That's why. So that's the for UI applications, there's basically always a main thread which is responsible for drawing the UI and shouldn't be blocked. So that's why there's a main scope and a coroutine scope, and activity itself is basically responsible for the UI, so it's a main scope should be used here. Alternatively, we can implement coroutine scope interface in the activity class, and implement the coroutine scope by coroutine scope and give it a dispatcher. The best way to do it is to use delegation with default factory functions. We also can compile the desired dispatcher. Here it is with the scope. Now we can launch coroutines in the scope of this activity without having to explicitly specify their context. That means when you run every coroutine, it's basically always, even in a function, declared coroutine is always launched on the coroutine scope, which is declared by implementing it of your class. In our main function, we create activity called test do something function. Where's that do something? Here it is. And destroy activities after 500 milliseconds. Oh, this looks so not Android. Anyway, it's just a demonstration. You create an activity. You create a class. And you call some function in it. And print launch coroutines. So you scheduled for a lot of 10 coroutines, and these coroutines should always be in the default, use the default dispatcher and under the coroutine scope of. So after that, if you have destroyed the activity, everything should be I don't know. I need a full code. Is everything cancelled in the destroy? Because this destroy does not hook to the cancellation of these coroutine scope. Where is it? Yeah, it calls cancel. So yeah, with that, the remaining. So we will probably run 3 or 2, maybe 2 coroutines here, and we'll see launch coroutine. Coroutine 0 is done. Coroutine 1 is done. Destroying activity. I don't know if the child would be cancelled as well, and because nothing is. Oh, this is just to live long enough to see if anything is going to be updated. So basically, we're going to see only launching coroutines 0, 1, and destroying activity. Oh yeah, it's shown here as well. Let's check it. Yeah, it's the same. So yeah, everything is destroyed after. Because in the destroy, your coroutine context, your coroutine scope is cancelled. So which is this cancel is probably inherited from this coroutine scope. So yeah, because all the coroutine that is launched in this class is cancelled. So only the finished one would be displayed, would be logged. So this is the very last part of this lesson. Thread local data. Sometimes it is convenient to have an ability to pass some thread local data, but for coroutines which are not bound to any particular thread, it is hard to achieve it manually without writing a lot of boilerplate. Yeah, but actually I nearly never pass some thread local data to a thread. That's not quite often in the Android world. For thread local as context element, extension function is here for the rescue. It creates an additional context element which keeps the value for the given thread local and restores it every time the coroutine switches. Okay, so this is basically just something it's going to. So the point here is coroutine can be run. The same coroutine can be run on several different threads. So keeping something in a specific thread does not seem to be valid, or it just doesn't work. So that's why we need this as context element here. If we thread local dot set main, and then pre-main current thread is something, whatever, and there's a thread local menu value which is main. And if we launch something on that, the thread local, we want to keep this thread local. So, but it is launched on another dispatcher, which is the default. So it runs on another thread. And also there's a thread local dot as context element value equals launch yield. Yield means give it to another. Oh my, this is complicated. So before main, the thread was main and coroutine number 1, 5. Where does this 5 come from? I don't know. But the thread local was main. And in a coroutine, we declare that the thread local to be we want to replace the thread local with as context element with this launch here, and that's this one. So where is this thread local? It's actually a Java one, so probably this is some extension for it. Yeah, it's an extension function of thread local, and that's how it is worked. So yeah, everything inside his is launch, and even, well, I don't know why it is yielding this. There's nothing changed here, but anyway. So after postman, this job is joined, so this line will not happen until this job is finished. So after that job is finished, we come into this post main current thread, and the thread local is again restored to that main. In this example, we launched new coroutine in the background thread pool using default. So it works on a different thread from a thread pool, but it still has the value of thread local variable. So what if we don't give it anything here? The thread local is going to be now. No. There's nothing. The thread local is going to be no. How about confined, because it's going to switch right on confined. It's going to be first run on main, and it is still run on main. I don't know why, because it's not. How about delay? Ah, there it is. Also yield. I don't know what's the purpose of this yield here, but what I want to check is this delay. So we can see that even if we are on different thread, main and default executor, and the thread local is always launch here. That's the point that this demonstration would like to make, I guess. Oh, there's an output with debug and oh, actually, yeah, without that, let's resume it to where it was. It's supposed to be worker 2, but it's not worker 2 here for some unknown reason. Maybe I should report this bug. Let me report this bug. di different running the does not yield the result of running differs one. In the tutorial, is expected, but I have received when executing the code, the worker before and after yield are the same. Where's the tutorial? Here. But running this I don't know why. Maybe they will go and they will answer me. So note how easily or one may forget the corresponding context element when then still safely access the thread local. It means that these two are different coroutines, different contexts or different dispatchers, which is part of the context. To avoid such, ensure parent and failfast on. Let's just ensure parent. Check whether current thread local is present in the coroutine context and throw illegal. Oh yeah, that's what I mean. It was no for when I just give it no thread local. So maybe to try that we can use, if we remove this, it's going to throw an exception probably. Suspend inline function because following candidates. What should I pass in? Oh, thread local dot in. And there's an illegal state exception. Thread local is missing from context. Illegal, where's that illegal? Yep. Thread local has first class support and can be used with any primitive provides. What does it mean by first class support? It has one key limitation. When thread local is mutated, a new value is not propagated to the coroutine caller, and updated value is lost on the next suspension. Use with context to update the value. I'm going to skip this. This is a little bit too hard. Alternatively, a value can be stored in a mutable box like class counter, which is in turn stored in a thread local variable. However, in this case, you are fully responsible to synchronize potential. Yeah, this is still too pro as well. I'm not going to cover these two. For advantage usage, even more advanced. For advanced usage, for example, for integration with logging MDC, what's MDC? Transactional context for any other libraries which internally use thread locals for passing data. See documents of thread context. Okay, I'm going to totally just skip this part. This is just too hard, at least for me. So if you like to help introduce what that means, feel free to leave a comment. So that's all for today. We have overtimed a lot today but I really want to finish this in 2 chapters. So that's all for today, and I think we have, after this, a lot of the mysteries of Coroutine should be solved now. So I hope that when I'm learning later, when we learn more about Coroutine, things should be more expectable, I hope. And that's all for today. See you next time, guys. Bye bye.